7 from here, but like it's 9.5 actually. I mean longer because we're going to chat through the 2,
Yeah.
so it's probably more like
Perspective.
I'm going to the night.
Please enjoy the votes while I later put something up there. Let's see. Okay, so last time we were talking about sources of opacity, sources of things which say to photons, thou shalt not pass, or at least some of them. And so we had talked about, last one was free absorption. We talked about bound absorption, bound free absorption, free absorption. I'll mention, because I don't think I did that, because I like the word so much, that the inverse of free absorption, the inverse of free absorption, and remember that's where you got an ion with an electron near it. The electron is not bound to it, but it can absorb a photon. And the ion is needed to conserve momentum because if all went well, you showed that you can't have a single electron absorbing a photon, because then you can't conserve both energy and momentum. It's directly related to the fact that the electron has no internal degrees of freedom. It's just a single particle. An atom can do it because it has internal degrees of freedom. Anyway, the inverse of free absorption is free emission. Or in other words, an electron accelerates, at least classically speaking, in the presence of an ion. In classical electromagnetism, accelerating charges radiate, and quantum mechanically that can be generalized. Free emission, and so you got an ion, and you have an electron, and this time, kind of where I've been, this isn't really that important, but you have a photon being emitted by the electron that accelerates in the presence of an ion. Instead of absorbed, emitted by a free electron as it accelerates in the presence of an ion. I guess I'll just say, in the presence of an ion. And it has such a good German name. This is Bremsstrahlung auf Deutsch. Or as American scientists will sometimes say, like Bremsstrahlung or something like that, or like Bremsstrahlung, meaning braking as in push the brakes on the car, radiation. Lots of things are more fun in German because, in English, Newton's second law, right? Or just kinematics. In English, acceleration is the rate of change of velocity, but in German, Beschleunigung is the rate of change of Geschwindigkeit. I mean, isn't that a lot more fun, right? Beschleunigung is acceleration, and Geschwindigkeit is velocity. So, anyway, another name for it in German. What questions do you have? Yes?
If the electron isn't bound to the ion, why does it being near the ion give it any more degrees of freedom?
So, well, again, it's essentially the idea here is you need something else around so that you can conserve both energy and momentum in this process. And if you, it's not right, but also if you look at it from the standpoint of classical electromagnetic theory, where you wouldn't be talking about photons, you'd just be talking about the continuous emission of electromagnetic wave. In that case, the picture would be, well, the ion is there to provide an electron that causes an electric field that causes the electron to accelerate, and accelerating charges. So it's just the fact that there's now basically like, two particles there instead of just one isolated by itself. You've got a multi-particle system, and that's the sense that we've got more degrees of freedom, so to speak. What other questions do you have? Okay, so finally there is number 4, electron scattering. Electron can't absorb a photon, but it can push it around, it can redirect it. Electron scattering occurs when photons are scattered by free electrons rather than absorbed. Photon never disappears, it just changes direction. They're scattered rather than absorbed. You may have noticed before, like when I turn on the what do you call it, discharge lamp, and it was glowing pink, the hydrogen discharge lamp. We looked at it with the diffraction grating, and we see the emission line spectrum, the 4 Balmer lines. You probably noticed that it wasn't just those 4 wavelengths that you can see, or 3 probably, because one of them was very dim. You saw other wavelengths as well. And I'll just point out, that's because photon emission and absorption by electrons jumping up and down aren't the only processes available in that too. There was Bremsstrahlung happening, for example. There was other sources of emission than just photons jumping up and down between levels. Electron scattering occurs when photons are scattered by electrons rather than absorbed. And this is also called Thomson scattering. And has this characteristic that the cross-section is independent of wavelength. And we'll say some more in a bit about how the other types depend on wavelength. But for Thomson scattering, it's always A pi over 3 times E squared over the mass of the electron times C squared. And this is the charge on the electron, not the base of the natural logarithms. This is the charge on the electron squared. The whole thing is squared. That works out to be 6.65 times 10 to the minus 29th power square meters, which is very small. That's much smaller than the cross-section of an atom, for example. But it's independent of wavelength. There's no wavelength dependence there. This becomes important deep in stars where everything is ionized completely, so that this actually dominates deep in the interior of the star. But other than that, other processes tend to be more important. Because of the way I was presenting this at the end of class last time, I didn't say anything about the bound-free cross-section. I will, which is why I'm saying C below here in my notes. We've already treated the sigma bound-free at this point, but I'm going to do it in a few minutes because I wanted to get through as much of this last time before class ended as possible. Sigma Thomson is much, much less than sigma bound-free, C below. So that Thomson scattering becomes dominant only in very hot stars where everything is ionized, or deep in the interior of any star. Thomson scattering dominates only in very hot stellar atmospheres. Where everything is ionized. Since it's so freaking hot. And also in stellar interiors where it's freaking hot and everything is ionized. But if everything isn't ionized, then what will tend to dominate the opacity is bound-free absorption, where electrons are already in atoms and they're kicked out, they're ionized from atoms. That tends to dominate in a region where you don't have everything ionized. What questions do you have? Yes?
I was saying that we can never really analyze a perfect spectra of something, because when we looked at the hydrogen plant, we saw other colors that we weren't really looking for. So does the same apply when we look at stars?
So when we look at stars, generally we see an absorption line spectrum. So they're dominated by, well, they're best described as a continuum spectrum with dark lines. And as we'll see, we can give different levels of descriptions of why the dark lines are there. The first level of description is to say the deeper interior layers of the star are dense enough so that they give a continuous spectrum, but the upper layers of the star are less dense. They're not, quote unquote, optically thick, and so photons at spectral line wavelengths before they make it out of the star are absorbed and emitted in different directions by atoms in the upper atmosphere. A more sophisticated approach is to consider how the opacity varies with wavelength. We'll get to that. But spectral lines correspond to wavelengths where the opacity is much larger because atoms are very good at absorbing photons at their wavelengths. And long story short, when the opacity is high, you can't see as deep into the star, which means you're seeing higher, cooler layers at spectral line wavelengths, and therefore the star is dimmer at those wavelengths because you're seeing cooler and thus darker regions of the atmosphere at spectral line wavelengths, whereas you're seeing deeper into the star outside spectral line wavelengths. I don't know if that answers your question, but it at least inspired me to say that.
I'm still a little confused.
Okay.
All
Yeah. What are you confused by?
So, if we are analyzing spectra, and let's say the star is not as opaque, and the spectra I see some dim colors as well, so would that be that it's just because the photons are getting scattered, or there are other elements present?
Yeah, no, so first of all, when you look at a star spectrum, it really is going to be, you're not going to see dim wavelengths. What I was talking about there would be more relevant to looking at an interstellar cloud, an emission region, where you're seeing emission lines rather than absorption lines. When we had that spectrum tube, you saw an emission line spectrum, not an absorption line spectrum. And so my point was really that at first, if all you thought could happen to emit those photons in that lamp was electrons recombining with atoms and dropping down to lower energy levels and emitting spectral line wavelengths, you might expect that from that hydrogen lamp, you would see the Balmer red, teal, and blue/indigo spectral lines, and that's it. You wouldn't see any other colors. But in fact, you do see weak continuum emission as well. And that's because of the fact that you can have brainstorm, you can have other emission processes, in addition to just having photons being emitted by electrons transitioning within atoms. And that was really my point there. It's not so relevant to the stellar atmosphere, where outside the absorption line wavelengths, you're mostly seeing continuing emission from the deeper, hotter layers. Now, that's contributed to by Bremsstrahlung and by free emission, and that is free emission, and by bound-free emission, no, sorry, that would be free bound emission, the opposite of bound-free absorption, and so forth. That's all contributing to the black body spectrum in that case.
It's clear now.
Yeah, and even with the tube, you can have electrons when they first get captured by the atom. They're not constrained to be at a spectral line wavelength because their initial energy is in the continuum, and so there's a spread of energies initially of the electrons that are being absorbed by the atoms, and so the initial photons given off are going to be at particular spectral line wavelengths when the electron recombines with the atom. And so in the tube you see more than just the 4 spectral lines over the Balmer lines. Okay? Anything else? Yes?
What's the subscript on the second sigma one?
Bound free. BF, bound free.
It's like an edge.
It's a BF. BF, yeah. Because after the electron, well, that's bound free, right? If it went from free to bound, afterwards they're best friends forever, they're BFFs. Right? So, but anyway, except they're not, because then somebody else comes and strips the electron off it again. They're very promiscuous, these atoms with their electrons. They're like, they fall in love, and then pretty soon they're like, I don't need you anymore, So, I'm very much anthropomorphizing that. Okay. Right. Back to bound-free absorption. If you remember, is also called photoionization. And it has an inverse, right? So if you've got bound-free absorption, what would its inverse be? Bound-free emission, right? Except we might call it free bound emission if you want to split the first thing. It's going from, the electron's going from free to bound. So you might say free bound emission, or you might say bound-free emission. The point being that you go between bound and free states. But if it's emission, it's going to be initially a free electron, and then it recombines with an atom to produce a photon. So yes, it does have that as its inverse. But back to bound-free absorption. For an H atom in energy level N, right, in other words, the principal quantum number is N. Just be sure you're following. What are the possible values of N? What's the ground state value of N? 1, and then the next up is 2, and then 3, etc. What are the energies of all the different states? So E sub N for hydrogen is minus what over what?
13.6.
Yeah, 13.6 eV over N squared. And so plus that is the ionization energy for that state, right? In other words, in the ground state, relative to N equals infinity, relative to the state where the electron and the proton have been separated, they're far from one another, and they're not moving, the minimum energy you need to ionize from the ground state to achieve that state is 13.6 electron volts. That would take you from minus 13.6 electron volts up to 0 electron volts. If you're, excuse me, if you're in N equals 2, then 13.6 over 2 squared is like, I think it was, what was it again? It's like 3.4 4 electron volts, I think is what that works out to be. If you're already in n equals 2, it only takes that number, which I think is 3.4 electron volts in order to ionize you, because you only have to jump from n equals 2 up to infinity, so to speak, up to being ionized. And so forth. So this is what we're referring to here. Bound-free absorption is a photon comes in, strips off the electron. That's easier and easier to do the higher the value of n, because the electron is bound less and less tightly for higher n values. If the electron's in the ground state and a photon of energy 14 electron volts comes along, could it ionize it? What do you think? Could it ionize it? It takes 13.6 eV to ionize it. Could 14 do it? Sure. Could 15 do it? Sure. Could 12 do it? No, right? Anything more energetic than the ionization energy can strip the electron off and ionize it. So for an electron in energy, for a hydrogen with this electron energy n, sigma bound free, right, which is our measure of how prone this is to happen, the cross section, works out to be 1.31 times 10 to the minus 19th power times 1 over n to the 5th power times lambda over 500 nanometers cubed. What are the units of a cross section? Square meters, right? Square meters. A cross section looks like an area. It's kind of how big a target does the atom appear to be to a photon. That's its cross section in square meters. This is what it works out to be with the understanding that the photon has to have enough energy to cause the ionization, right? In other words, it has to have at least energy photon must have at least energy of plus 13.6 electron volts over n squared, because that's the ionization energy, which is the minimum energy you need to produce an ionization. Ionization energy for electron in n. It's quantum, it's physical quantum number is n. So the photon has to have at least that much energy, and then if it does, you plug into the formula. The cross section is 0 if it has less energy than that, because it can't cause the ionization. But as long as the photon has enough energy, this is how it goes. So notice that there's an n dependence there. Larger n produces a smaller cross section. And also that it depends on the wavelength cubed. But as long as you've got enough energy, you can cause the ionization. And notice too that you got a 10 to the minus 19 here, you got a 10 to the minus freaking 29 over here, which is why we're going to find that the Thomson cross-section is much smaller than the bound-free cross-section. And so if there are electrons bound to atoms, then you're going to get more of the, you're going to get more interactions of photons coming in and ionizing atoms than you are of photons just scattering off of electrons. Okay? What questions do you have? Let's explain why the sky is blue, shall we? I'll mention this here. Why is the sky not blue? As in, what do parents everywhere tell their children, probably believing it, but it's just totally BS? Yes.
Like the ocean?
Yeah. It's not because it's reflecting the freaking ocean. The sky is not blue because it's reflecting the ocean. How would the sky be blue in Ohio because the sky is reflecting the ocean? I asked you, that's ridiculous. No, that's not what's going on. The ocean looks blue on a bright and sunny day because it's reflecting the sky. It's the other way around. Photons can also scatter from loosely bound outer electrons in atoms. Electrons, I'm going to use E minus to mean an electron. Loosely bound outer electrons in atoms, which is called Compton scattering if the wavelength is much smaller than the size of the atom. Now, to be honest, I've also heard Compton scattering being used to describe scattering off of free electrons. So I think there's some ambiguity as to the terminology there. It's called Compton scattering. If the wavelength is much, much smaller than the size of the atom, and Rayleigh scattering if the wavelength is much, much greater than the size of the atom. So for visible light, which regime are we in? Are we Compton scattering or Rayleigh scattering? How big is an atom? How big is an atom, roughly speaking? Oh, man, we're supposed to burn this into your brain. Wow. No smoke coming out of your ears because it was never burned into your brain. How big's an atom? Yes?
Roughly a radius of 10 to the negative 10?
Yeah, about 0.1 nanometers. An atom are around 0.1 nanometers for the size of an atom, give or take. Visible light, lambda's around what for visible light? Give me a typical wavelength. What do your eyes like to see, so to speak? Around 400 to 700, so about 500 nanometers, roughly speaking. 500 nanometers, 400 to 700. Which regime are we in? Is the wavelength much, much bigger or much, much smaller than the size of the atom? Much, much bigger, right? So we get Rayleigh scattering for visible light. Compton scattering is going to be like X-rays. Now, I'm not going to prove this, but I'm going to state the following very important fact. The Rayleigh scattering cross-section is proportional to 1 over lambda to the 4th power. So it's like 1 over lambda to the 4th power. So what happens as lambda gets shorter? Does it scatter more or scatter less? It's 1 over lambda to the 4th power. Do you get more scattering for longer or shorter wavelengths? More for shorter wavelengths, yeah. So short wavelength light is scattered much more than long wavelength. I mean, we don't get a full span of the doubling in the visible spectrum, but this is saying that sigma for 700 nanometers is, because that would be the long wavelength kind of cutoff right for our eyes, is only blah sigma 350 nanometers, right? So that's in the ultraviolet, but it's close to what we can see. Sigma for 700 nanometers is what fraction of sigma for 350 nanometers? What happened to the wavelength if I go from 700 to 350? What did I do to the wavelength? Yeah, it's half as big, so what happens to the scattering cross-section? Goes like 340. Yeah, it's only 1/16 that at 350 nanometers. So, okay, that's a bit into the ultraviolet, but still, red light scatters a lot less than blue and violet light does, is what it comes down to. Blue light scatters much more than red, yellow, orange light. This is why the sky is blue. This is why. Because idea is that what color would our sky be if we had an airless world?
What?
Black, right? Why is the sky black on an airless world?
There's no atmosphere.
There's no atmosphere, and so if we were standing on the moon, here's a photon from the sun that, it flies over my head, and there's no reason for it to get into my eyes. The only way I can see a photon is if it gets into my eyes. So if we're on the moon, there's all these photons from the sun flying over our heads, not getting into our eyes. Now, if I throw up a tennis ball, I will see some of those photons because the tennis ball redirects them to my eye. Alternatively, if I'm on Earth and there's this atmosphere above me, lots and lots of molecules can Rayleigh scatter photons that were going to miss me, they were just going to fly over my head, but whoops, some of them get scattered into my eye. So I look up, I'm seeing Rayleigh scattered photons hitting my eye, they're going to completely miss me. Are there going to be more red ones or blue ones that are going to be Rayleigh scattered into my eye, given all of this? Blue ones. Rayleigh scatter is much stronger for short wavelengths than for long wavelengths. And so if I had color filters that only let in some narrow range of wavelengths, if I put a red filter in front of my eye, I'll see a red sky. And if I put a blue filter in front of my eye, I'll see a blue sky. But that blue sky is going to look a lot brighter than that red sky because there's a lot more blue photons being scattered than red or orange or yellow photons. All the colors are scattered by the sky, but blue and violet are scattered more, and so the sky looks blue. Well, there's I think it was XKCD had this question in there where this kid asked this and the person was like stammering or whatever. Okay, violet is scattered more than blue is. How come the sky isn't purple? Yeah.
Is it because the sun is like, I'm going to word this horribly, but it's giving off more like green light than...
Yeah. So part of it is that the sun gives off more blue photons than violet photons, right? And the other piece is, what about our eyes? We are, most of us, trichromats. Some folks, because they're colorblind, are closer to being bichromatic instead of trichromatic. Now, the most common type of color blindness is red-green blindness, where you still have 3 different cones sensitive to different wavelength ranges, but there's a mutation for people. For most people that are red-green colorblind, there's a mutation such that the red and green cones the pigments, their wavelength ranges overlap more than they're supposed to. So effectively, they have two-color vision because it's not quite true. They do still have three-color vision, but there's not much distinction for them between red and green because the sensitivities of the long and medium cones. We used to say red, green, blue, now we just say long, medium, short because it doesn't correspond that well to color, so they're pretty broad responses and all that. Their long and medium cones are too similar to one another in terms of those pigments, spectral sensitivities, and so it's harder for them to distinguish red and green. But overall, we have our color vision. We've got three types of cones, long, medium, and short. Roughly speaking, red, green, and blue sensitivities. We don't have violet sensitive cones per se. So in other words, our eyes are also more sensitive to blue light than they are to violet light. And so the sky is blue, both because the sun gives off more blue light energy and because our eyes are more sensitive to blue light than they are to violet light. So the sky looks blue as a result of that. This is why the sky is blue. When you look up into the sky, you're literally seeing the atmosphere, not figuratively, you're literally seeing the atmosphere. You're seeing light scattered by air molecules. It would look black if it wasn't there, so you're literally seeing air, and that air looks blue because of ray scattering, because it scatters shorter wavelengths more than longer wavelengths. Every college educated I think everybody should know this, but certainly college-educated people should know this, and freaking certainly astrophysics majors ought to know this at some point. So you're going to tell your kids the real reason why the sky is blue someday. Yes.
The ocean.
What was that? Because of the ocean.
By the same reasoning, can you explain why the sun appears blue on Mars?
Yeah, so a couple of things. So first of all, and I'm going to do this again later, when we get to interstellar rending and stuff like that. Why is the sun red at sunset, roughly speaking? It's because the sun, on Earth, it's because the light has to pass through more atmosphere. And so that longer length of atmosphere, remember we're talking about plane parallel atmosphere and the zenith angle and all that. So when the sun is low in the sky, it passes through a longer length of atmosphere, meaning a larger fraction of the short wavelengths have been scattered out of the beam of radiation, and preferentially longer wavelengths from the sun are what make it to our eyes. And so the sky is blue and sunsets are red or orange or whatever for exactly the same reason. It's all wavelength scattering, and also it's called me scattering by dust particles. Me scattering is scattered by dust particles. It's also stronger at shorter wavelengths, but it's more like 1 over lambda instead of 1 over lambda before. So me scattering doesn't cause this distinctive coloration as Rayleigh scattering does for those larger particles like that. Anyway, on Mars the sky is red because of the fact that the Martian atmosphere is full of pigmented dust particles. The Martian soil has rust-like compounds in it. And so the Martian sky looks red because the dust is actually colored, it's pigment. And so it's literally reflecting more red light to your eyes if you were on Mars, and so it looks reddish. But that means sunsets on Mars look bluish because more of the red light is reflected out of the beam, and so a greater portion of the blue photons reach your eyes. And so I think it's just awesome that on Earth we have red sunsets in a blue sky, and on Mars we have blue sunsets in a red sky because of the difference in the dust particles in the Martian atmosphere. If you got rid of the dust, the Martian atmosphere would be like a deep bluish color because its air is very thin, but you would still get Rayleigh scattering and give it a bluish tinge to it, but it's much darker because the air is so thin. Fun with physics! Woo! Okay? All right. What questions do you have? Any further? Let's continue then, shall we? So, for an H atom in the n=2 state, those are very popular with us, remember, because H atoms with the electron in the n=2 state are what we need to get what kind of spectral lines? What series of hydrogen spectral lines as the electron starting or ending in n equals 2, the first excited state. So if it's in the ground state, that's the Lyman series. So if it's in n equals 2, why, there was a Swiss high school teacher that he's got named after, Johann Balmer. The Balmer series spectral lines need hydrogen atoms in n equals 2. So, right, remember Goldilocks and the 3 stars and all that business. And for that matter, Cecilia Payne and the Boltzmann and Saha equations and all that kind of stuff. So we like atoms, H atoms in n equals 2. They're the ones that give us Balmer series spectral lines. Here's another thing that they're responsible for. For an atom, an H atom, in n equals 2, the ionization energy, and I was right before, I didn't remember, ionization energy is chi2 equals plus 13.6 eV over 2 squared. That's how much, that's the energy of n equals 2 is minus equals 3.40 electron volts. In n equals 2, it's 3.40 electron volts below energy 0. So to get it up to energy 0, to get it to just barely ionized, takes 3.40 electron volts. So any photon with at least that much energy, or put another way, any photon with wavelength less than or equal to the wavelength that would produce 3.4 eV of energy. Lambda is less than or equal to hc over chi2, right? Because hc over E is the energy of a photon. Right? H is the wavelength of a photon. Any photon with wavelength shorter than the wavelength that has that much energy, 3.4 electron volts. What's hc equal to? Why, that you just burn that into your brain too. You're all just going to be like, hc is how many electron volt nanometers? 12, not 12.4, 1240, it's 1240. Yeah, 1240. And what's a factor of 100 here? 1240 EV nanometers over 3.40 electron volts. Why, that's going to be 365 nanometers. Why, you get yourself a nanometer for every day of the year. What a bargain, right? 365 nanometers can ionize it. Any wavelength shorter than 365 nanometers can ionize it. 365 nanometers. What part of the spectrum is that in? Wait a minute. So visible range is 400 to 700, right? But this is shorter than 400. So it's not visible. It's close to visible. Is it IR or UV? UV, because it's shorter than any visible wavelength. Right? 400 is the violet end. Can ionize it, right? So this is in the near ultraviolet. It's in the near ultraviolet. Any wavelength shorter than that can ionize it. So the continuum opacity meaning opacity that isn't restricted to spectral line wavelengths. Continuum opacity is where the opacity is varying smoothly with wavelength. The continuum opacity jumps below this wavelength. Right? So in other words, you can imagine like you're plotting, this is going to be super rough here. Here is sigma, or no, here is kappa, and here is wavelength, here's 365 nanometers, it'd be like, oh, okay. If I go below that wavelength, whoop, you get a spike because of the, I think it's starting to fall down again. This is super, I'm just making that up. But in other words, there's a jump when you go below 365 nanometers, because now there's this channel of absorption available. You can ionize hydrogen in N equals 2, so the continuum opacity jumps up below that wavelength. It's bigger at less than 365 than it is at more than 365. The continuum opacity at 370 nanometers is smaller than at 360 nanometers, because at 360 nanometers, hydrogen in N equals 2 can absorb those photons via photoionization. So all of a sudden, in other words, there's an additional contribution to sigma bound free below that wavelength. Due to the new contribution to the bound free opacity below that wavelength. Make sense? Questions, comments, observations? Doing observations with UV filters is tricky because atoms tend to like to eat UV photons because of things like this. And so you can get all sorts of complications as a result of that. And we'll take our break here. That is several minutes. Well, that's like an hour and 4 minutes fast because of daylight saving time, and it's just fast. Yes? Kappa. That's a Greek letter, kappa. Yes.
What would you say about quantum scattering? So you mentioned that.
Yeah, so Compton scattering is what you call it when the wavelength is much smaller than the size of the atom, and given that atoms are only like, on the order of a tenth of a nanometer, those are going to be very, very energetic photons. They're going to be like X-rays and gamma rays, what we're talking about. Whereas Rayleigh scattering, we're talking about ultraviolet, visible, infrared, and so on and so forth.
On the side, there's lots of pictures of Rayleigh scattering whenever I see it.
Yes, yes.
Yeah.
It's so beautiful.
It is.
Yes.
It's magnificent.
Yes, I love to walk out and enjoy me a lovely Rayleigh scattering, as a matter of fact. Yes.
And it looks even more special when you're on plane and you see it everywhere across the horizon.
Yes, yes, indeed you do. And you see the fact that if you're high enough, that the sky gets darker as you look higher up because there's less air above you. And so there's not much coming your way.
Beautiful gradient of colors.
Indeed, that's right.
And Earth's not flat, it's confirmed.
That's correct, yes. Believe it or not, yes. And I believe it. Yes, Earth is a sphere. Yes, right. And so one can relay the beauty of Rayleigh scattering. Yes. Yes.
They're free. 14 feet. That's
So is it that the absorption
Yeah, they found somebody who sounds a lot like James Earl Jones to do the voice of Darth Vader. Pretty impressive. Because sometimes, they'll dub things and it's like, who is that? It doesn't sound anything like it, of course, the people are usually saying it in English.
holiday special.
And I do have to say, do y'all know Peppa Pig? Yeah. Oh, so much better in Italian. Just so much better. Because in Italian, she's Peppa Pig. Oh, it's just awesome. I've seen both the English and the Italian. So much better in Italian. I totally prefer Italian Peppa Pig. It's like, Peppa Pig, Ed George. It's like Just, I think that's part of the humor, it's like all these, and George, you know. Yes. Okay, anyway, back to our story. The primary source of continuum opacity in most stars is the H- ion. And we will see this again and again. It's just so important. Primary source of continuum opacity that varies smoothly with wavelength. There might be some jumps, but in general, varies smoothly with wavelength. The primary source of continuum opacity in most stars is the H- ion. It's the reason the sun looks like it has a sharply defined surface. Right, so that's going to be H with 2 electrons, because you can actually bind an extra electron to a hydrogen atom. This is not unusual in an ionic solid, right? That's essentially what's happening. Is not an ionic solid. If you dissolve salt in water, so the solid's kind of like this, but if you dissolve salt in water, sodium chloride, you get Na plus ions and Cl minus ions. The chlorines, a chlorine can, what am I trying to say? The chlorine will attract that electron more than the sodium atom will, and so chlorine will bind with an extra electron. You get Cl minus. Well, H minus exists too. It has a certain electron affinity, the ability to bind 2 electrons rather than just 1. And more electrons than protons. So it's H with 2 electrons, but there's only one bound state for that extra electron, and it's only loosely bound. It's easy to detach. Its ionization energy, the energy needed to strip that extra electron back off again, is 0.754 electron volts. So that's the electron affinity, that's how much energy that will be given off if you bind that extra electron. And the opposite of that is the ionization energy, 0.754 electron volts. And thus can be ionized by photons with lambda is less than or equal to Hc over chi for the H minus ion there. What's Hc again? 1240 eV nanometers. This time we're going to divide by 0.754 nanometers and get us 1640 nanometers. What part of the electromagnetic spectrum is 1640 nanometers in? Is it visible? Is it shorter or longer than visible? Wait. Visible is 400 to 700, so it's longer. And so what part of the spectrum is that? It's a bit longer than visible, so it is infrared. Infrared, yeah, that's an IR wavelength. Every visible photon has enough energy to cause this ionization. Every visible light photon can cause this ionization. So this opacity exists for the entire visible spectrum. And did a homework problem where you're looking like the continuum opacity. How far could you see in Earth's atmosphere if the continuum opacity was the same as for the sun. Well, H minus is really what you were looking at there. H minus is the primary contributor at visible wavelengths to the solar continuum opacity. And you should have found that you could see about 30 meters in Earth's atmosphere if it were as opaque, at the same opacity as the sun. 30 meters is, like 90, 100 feet or thereabouts, which, okay, we could certainly navigate this room, although you all would be looking a little bit fuzzy to me. You don't want to drive when the visibility is like 100 feet, right? Because you're going to ram into the car in front of you if it breaks and you didn't see it in the fog and all that. In the sun, because it's so much less dense, the solar atmosphere is so much less dense, the visibility, instead of being like 100 feet, is more like 400 kilometers or thereabouts. We can see to about 400 kilometers in the solar atmosphere if you were transported there, and avoiding the whole going blind while vaporizing issue, right, that you would have if you were there. But it's only the lower density that allows that, and again, I think I've mentioned this before, 400 kilometers is great visibility in our atmosphere, right? You can fly all you want with 400 kilometers visibility, that'd be fantastic. But on the sun, 400 kilometers is such a tiny fraction of the sun's size that it's why the sun looks like it's got a sharply defined edge, because that is so thin compared to the sun's diameter that all the light's coming from an exceedingly relatively thin layer. If you were right up to the sun, you could see it's fuzzy. But back where we are here, that looks very sharp. And so the sun, that's why the sun gives the illusion of having a solid surface. It's why it has a well-defined photosphere, sphere of light, where all the light seems to be coming from as it last scatters going into space. It's the H minus ion that is responsible for that primarily. Yeah, do you like you had a question maybe? Oh, okay, you were just like doing something. Did anybody have a question? I'm just okay. All right. So H minus. We'll keep coming back to H minus as we go along. For example, in low metallicity stars, so what makes H minus? Well, you need to have a supply of extra electrons around to bind with those hydrogen atoms. Where are those extra electrons going to come from? From metals, from heavy elements that hold their outer electrons more loosely than hydrogen does. A pure hydrogen atmosphere is going to have H minus, because if you ionize a hydrogen atom to get a proton and an electron, that electron is going to find the next bare proton and connect with that. It's not going to bind with a neutral hydrogen atom when there's protons around you could bind with. So you're not going to see H minus in a pure hydrogen atmosphere. But in an atmosphere that has metals, heavy elements that are relatively easy to ionize, then you've got this supply of extra electrons. In the sun, there's very little ionization, almost no ionization of hydrogen. So you got all these neutral hydrogen atoms and electrons that got stripped off of metals that can combine with neutral hydrogen atoms to make H minus. And so H minus is important in an atmosphere where it's cool enough that the hydrogen stays neutral and there's metals that are producing free electrons because of very weakly holding their outer electrons attached to them. So if you have a star with low metallicity, there won't be as much H minus, and so its atmosphere will be more transparent than the sun's atmosphere, or in general, more transparent than the atmosphere of a star with higher metallicity. So you can see deeper into the atmosphere of a low metallicity star, which makes them appear hotter than high metallicity stars of the same luminosity. And this is the reason why there is the subdwarfs, why we have low metallicity stars lie on main sequence, which is shifted a little bit towards higher temperatures relative to solar metallicity stars, because their atmospheres are more transparent, you can see deeper into them where it's hotter, etc., etc. So by the way, H minus is super important. Okay, onwards and upwards. The total opacity is the sum of the opacities due to all of those sources. capacity is the sum of these four contributions. So in other words, kappa lambda is kappa lambda bound plus kappa lambda bound free plus kappa lambda free plus kappa electron scattering. Why didn't I put a lambda subscript for the electron scattering? No, it's still photons that are scattered from those electrons, but we said something about electron scattering and its wavelength dependence before. Oh, you've already forgotten from the beginning of class. How does electron scattering depend on wavelength? It doesn't, so I don't put a lambda there because it's constant, it's independent of wavelength. That's a mess. That's a very complicated function of wavelength. The bound opacity spikes at every spectral line wavelength. Right? Wherever there's a spectral line wavelength for any atom, that has a spike in it. So if I was making a plot of kappa lambda versus wavelength, it's like la la la, spike, 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 spike. There's all these spikes in it because of kappa lambda bound. Ah, scary. Yes?
Is that those four or these four contributions?
The sum of these four contributions. Yes.
Or
Yeah, F-O-U-R, four.
you put it as four, so I was confused.
Wait, where?
Four.
Oh, no. My God, can't you read? This is an O-U-R, right? That's an O, that's a U, that's an R. No, that's a U. Shut up. No, not an A. Come on. There you go. O-U-R. I'm not showing that to my wife because she'll be like, it looks like an A-R. Okay. All right. She's never seen that. Those four contributions is what I'm saying there. Right? The bound free. Jumps at lambdas corresponding to ionization energies. As soon as you go below the wavelength corresponding to some ionization energy for some species, you get a jump because now you can ionize that species with wavelengths below that wavelength. So that's a very complicated function of wavelength, and for that matter, density and temperature. Yeah. Since capital lambda is a very complex, I should say complicated because I don't want to imply complex numbers. A very complicated function, maybe like capital lambda of density, temperature, and composition. And even this would be a simplification here, but I think we've said this before. Capital X, what do astronomers use capital X to stand for composition-wise? It's the mass fraction of hydrogen. So this is the hydrogen mass fraction, the percentage of the material by mass that is made of hydrogen. For the sun, it's about 70%. So X is about 0.7. What is Y? What mass fraction is that? Helium, yeah. This is the helium mass fraction. Leaving what is capital Z there? That is the, yeah, for metals, yeah. Metals, in quotes, mass fraction. In other words, the fraction of everything else. So Z is 1 minus X minus Y, because they should add up to 100% of 1. And so subtract hydrogen and helium and you get everything else. Z is always no more than about 4%. So we get away with just kind of just saying Z. Really, you want the mass fraction of every freaking species. What's the mass fraction of praseodymium? What's the mass fraction of ytterbium? What's the mass fraction? All that stuff, right? But because the Z is small, we can just kind of lump it all together. So anyways, this complicated function of density, temperature, and composition, in other words. Since it is a very complicated function of density, temperature, and composition, if you're going to make a stellar model, you don't want something that icky, messing up your complications for radiation transfer. So what do? We simplify by using a wavelength averaged Rosalind mean opacity. Rosalind mean opacity. Guess who it's named after? Yeah, after Dr. Rosalind. And it's got this complicated, funny-looking definition, and I've never bothered to see exactly why it's defined that way, because every year I think, I should finally look up why Rosalind mean opacity is defined the way it is. It's in your book with the definition, and I just never do it, you know? It's like, yeah, it's not raining anymore, I don't have to fix the roof, you know? So this is about the time of year when I say, I should really look that up, and then, yeah, but then I won't be grading their homeworks or whatever. So someday I'll look it up. Why it gets that funny definition. Your book just says here it is. I'm not even going to write it here. And so, in other words, we use this approximation. We say there's this kappa bar, average, wavelength average thing for the Rosalind mean opacity, which is some function of density, temperature, and composition. Now, you can't use kappa bound in this because it's, again, so complicated. It keeps jumping every time you're at a spectral line wavelength. It's just a mess. Yes?
Why is C equal to 196 minus 1?
Because these are the mass fraction of hydrogen, helium, and everything else.
Why is it that 1?
Because they add up to 1, in other words, 100%. It's a mass fraction. So if it were pure hydrogen, 100% of the mass would be in the form of hydrogen. In other words, we're using 1 to mean 100%. It's all there, right?
So you're subtracting mass fractions from 100%.
Yes, that's correct. That's right. Yes. Yep. Yeah. Because what we will do is we will say like x equals not 70%, we would say x equals 0.7. So if x is 0.7 and y is 0.28, that adds up to 0.98 of the material is hydrogen and helium. So how much is everything else? 0.02 add up to 100%. Yep. The many contributions to kappa bound can't be handled this way. So there you have to be more specific if you're really interested. But For kappa bound free and kappa free free, Rosalind means approximation formulae have been developed. Approximate formulas have been developed. And then I'll let you in on the secret. The authors, when they talk about this in the textbook, they're quoting Ava Novotny's textbook from the early 70s that I used when I was an undergrad because Carol and Osley hadn't been written yet. And so if you look at the references, you'll see it mentioned there. They got these formulas out of Novotny's book. So anyway, kappa bound free, Rosalind mean, is 4.34 times 10 to the 24th power times GBF over little t of density and temperature times capital Z, the metallicity fraction, times 1 plus X, 1 plus the hydrogen fraction, times the density over the temperature to the 3.5 power. And remember that an opacity has units of meters squared per kilogram. In other words, absorption cross-section per kilogram of material. Look, isn't it beautiful? It's just like so inspiring there. And meanwhile, and I'll say what all this stuff is in a second, kappa Rosalind free opacity is 3.68 times 10 to the 23rd power G free times 1 minus Z times 1 plus X times rho over T to the 3.5 power meters squared per kilogram, again, of stellar material. Okay, so we've got some explaining to do. What the hell is this? Now, I will say that the most important thing for us is this bit right here. Rho over T to the 3.5 power. That's going to be what we emphasize. But let's say a little bit about these monsters that are hiding there. So, GBF and GFF are Gaunt factors that provide quantum mechanical corrections to similar classically derived formulae. It's like, oh, it's all so clear now, right? They are that provide quantum mechanical corrections to similar classically derived formulae. The bottom line is we're not really going to be using these things in detail. We're just mentioning them. And then I'm going to emphasize that the rho over the T to the 3.5 dependence is what's really important for us. Like, for example, if you're studying maybe pulsating variable stars, then in an ionization zone where it modifies how the temperature varies with density as the log rises, why that changes how the opacity goes, and so why that might be important to you to understand, for example. There are quantum mechanical corrections are these factors which provide quantum mechanical corrections to similar classically derived formulae. And in practice, these things would be in a computer code. These would be stored in the form of lookup tables that your code is able to use. Why? Like if you're doing a project that involves, say, some sort of sophisticated stellar simulation software, why you would have lookup tables in there that you can interpolate in order to use these things, or at least the code can do it. Anyway, little t of density comma temperature is, I love this, it's a guillotine factor. Guillotine factor as in chop. It's a guillotine factor describing how an atom's contribution to the bound-free opacity is cut off after it is ionized from one stage to the next, so that that avenue of absorption goes away. It's a guillotine factor. And so it's going to be complicated. Because it's again going to have a wavelength dependence to it. It's kind of suppressed here, but there's going to be this wavelength dependence because it's kappa bound free. I'm sorry. Now I got to think about it. It's not going to be, ultimately that's wavelength dependent, but it's, I'll shut up now. But it has to account for the fact that it's doing it. So I have to think of what it will time. Anyway, so it's just contributing to the overall wavelength average value. So as the temperature goes up and the ionization changes, this will reflect that because various atoms are changing their ionization level and therefore changing the channels by which they are able to absorb photons, so to speak. So it's a guillotine factor describing how an atom's contribution to kappa bound free is cut off after it is ionized from one stage to the next. Describing how an atom's, some particular species, contribution to the crossing the kappa bound free is cut off. Cut off, and it's guillotine, cut off after it is ionized from one stage to the next. So let's see if we can develop a little intuition here. The contribution to the bound-free opacity from helium-1 is cut off for T above what value? Do you remember when you were doing those homeworks and we were talking about it and so forth? If I'm going to cut off the contribution from helium-1, so how does it contribute to the opacity? Helium-1, is that neutral helium or ionized helium? Neutral, right? Because 1 is 1 more than the number of electrons this can remove. So you got helium-1. How would it contribute to the bound-free opacity? Well, what's the easiest way? It's for it to lose 1 electron. Right? Photon comes along with enough energy to ionize it, to strip off 1 electron. So as long as you got plenty of helium-1 around, there will be opacity caused by, bound-free opacity caused by photons with enough energy to strip an electron off of helium-1. And when you wavelength average all the opacities from everything, That's making a contribution to the Rosseline opacity that will get guillotined for a temperature above about what? When does helium-1, just because of the temperature, kind of go away and become helium-2 instead? About what temperature was that? Around? So it starts with a 1. Yeah, and it's actually, that's hydrogen, right? Hydrogen 1. For helium, it was more like a little bit more. Still starts with a 1, but it's not 1, 0, 0, 0, 0. It's about 15,000, yeah. For more than about 15,000 Kelvin, right? So the Rosseline opacity will have a dip above about 15,000 Kelvin because helium-1 stops being a way to produce opacity. Helium-1 stops existing because most of the helium is now helium-2. So you don't have neutral helium atoms absorbing photons to become ionized to helium-2 because the temperature, collisions and so forth have gotten rid of the helium-2. Since helium-1 becomes helium-2 above this temperature. So there will be a drop in the bound-free opacity because you no longer have that channel, so to speak. You don't have helium-1 contributing anymore. And then for helium-2, what's the temperature where helium-2 gets ionized to become helium-3? About 40,000 Kelvin. So, pick your ionic species, and there will be these temperatures corresponding to its various ionization energies, where the guillotine function factor comes in and says, oh, there's a drop in opacity above this temperature because that ionic species goes away, or a rise in opacity because this ionic species becomes prevalent, that sort of thing, right? In other words, above 15,000 Kelvin, there's more helium-2 around. So the helium-1 opacity goes down, but the helium-2 opacity goes up because now everybody's mostly helium-2, et cetera, et cetera. Did I mention this stuff is complicated, right? That's because of all those kinds of considerations. For electron scattering, the Rosseline opacity for electron scattering works out to be 0.02 1 plus x meter squared per kilogram. And then my notes say, discuss figure 9.10. That would be the one that's been hovering there on the screen. Let's discuss figure 9.10, shall we? Yes, we shall. Are you as excited as I am? Yes, yes, we're going to discuss the Rosseline opacity for 70% hydrogen, 28% helium, 2% metals. So, first thing that's important to realize is that, see, there's multiple curves on there. That's not the Rosseline opacity, it's Rosseline opacities for different densities. So the curves are labeled with the base 10 logarithm of rho in kilograms per cubic meter. So in other words, look at this curve right here, the one that I actually attach numbers to as an example. It's labeled with -6. So this particular curve, where I've got 3s and 4s, red arrows pointing to it, 1, 2, et cetera, what density is that a plot of the Rosslyn opacity for? How many kilograms per cubic meter? -6 is the logarithm of the density in kilograms per cubic meter. So if -6 is the logarithm of the density, what is the density? Remember that the logarithm of a number is the power to which 10 must be raised to get that number. So to what power must I raise 10 to get 10 to the -6? -6, right. In other words, the curve labeled -6 is for a density of 10 to the -6, because the logarithm of 10 to the -6 is -6, because the logarithm of the number is the power to which 10 must be raised to give that number. What's the logarithm of 1,000? 3, because 10 to the 3 is 1,000, right? So if I say the logarithm of 1,000, you got to think about it for a minute. Let's see, 1,000 has 10 to the 3rd power, so its logarithm is 3. But if I say, what's the logarithm of 10 to the 3, that should just be meter, because the logarithm of 10 to the 3 is 3. Because I just told you, 10 is raised to 3 to give that number. That's the logarithm of the number, the power, right? What's the logarithm of 10 to the 57th power? 57, right, etc. So, this is the plot for a density of 10 to the -6, 10 to the -4, 10 to the -3, 10 to the -2, 10 to the -1, 1 kilogram per cubic meter, 10 to the 0, 100, 10,000, a million kilograms per cubic meter. So these are whole families of curves, okay? That's one thing to realize. Another thing, I sadly erased it, but remember that for kappa bar, bound free and free free, those are equal to blah, 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 rho over t to the 3.5 power. Density over temperature to the 3.5 power. A rho over t to the 3.5 power dependence is called and as far as I know I'm saying this correctly, it's one of these deals where it seems like, nobody's ever sure how to say these things. Somebody is, but I hear different ideas here. It's called a Cramer's opacity law. Because notice that the S is part of the name. So it's not Kramer's law, it's Cramer's apostrophe law, if you like. This is the Cramer's opacity law. And again, maybe it is Kramer's, but I think it's Cramer's, which sounds more sophisticated anyway. So let's decide that his name is Cramer's, even if it was Kramer's. Cramer's opacity law. So notice, again, too, that the opacity is cross-section per kilogram of material, which itself is depending on how many kilograms per cubic meter. So in other words, the cross-section per kilogram increases with the density. So overall, the opacity has a rho squared dependence because there's one power of rho from the fact that it's cross-section per kilogram, and another power from the fact that there's the rho in that as well. So increasing the density in terms of the opacity per unit length has a square effect. So, following the narrative in your book, I've helpfully, unlike the book, put these lovely red labels on here, and I passed out the slides last time so that you don't have to write all this down, and it's in my slides online too, so you don't necessarily have to write all this down, you have to know this here. And on the final, I would want you to explain these contributions, not on the upcoming exam, but on the final, I would want you to qualitatively explain these contributions. So, at low temperature, the free opacity is small because few atoms are ionized, and kappa bound free is small because bound free is, you gotta have enough energy to kick the electron off the atom. At low temperatures, the radiation field, photons, don't have enough energy to ionize in the body. And so the opacity tends to be very low at very low temperatures. This is the logarithm of the temperature, so this is like, you know, below 10,000 Kelvin here. The opacity tends to be low because those contributions are both low. But notice that as we increase the temperature, all the curves, these chop off there. It's not that they wouldn't continue, it's just that they're just left off. But as we go to the 10 to the minus 6 curve, which would be more appropriate like in the stellar atmosphere, at higher densities you're getting deeper and deeper inside the star. As we increase the temperature, the Rossellini opacity starts to rise because of the ionization of hydrogen and helium, so that there's more free opacity as a result of that. So that causes a rise in the wavelength average opacity. For 10,000, and then look at where it's labeled 3 here. That means this region here is region 3. For 10,000 Kelvin, right? Where's 10,000 Kelvin on the x-axis here? Tell my hand to stop when it hits 10,000 Kelvin. La 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 la. 10 to the 4th power, right? 10,000 Kelvin. For 10,000 Kelvin is less than T is less than 40,000 Kelvin. Well, this would be, it's a logarithmic scale, and so this would be about, if you look at a logarithmic scale, halfway between about 3-ish, so this is about 30,000 Kelvin here, so there's 40,000 Kelvin, about right there. Between 10,000 Kelvin and 40,000 Kelvin, hydrogen-2, ionized hydrogen, and helium-2, singly ionized helium, predominate because, remember, that hydrogen in a stellar atmosphere ionizes at about, or within a star in general, it ionizes at about what characteristic temperature? Hydrogen ionizes at about hydrogen ionization zone, Goldilocks in the 3 stars. Yeah, make it more approximate than that. I mean, yeah, it's about 10,000 Kelvin as opposed to 9920 or 96, whatever, right? About 10,000 Kelvin. For 10,000 Kelvin to 40,000 Kelvin, H2 and helium-2 predominate because helium-2 becomes predominant at about what temperature? Not 10,000 Kelvin, but a little higher, at about 15,000 Kelvin, right? So about 15,000 Kelvin. So, okay, 10,000 Kelvin to 40,000 Kelvin, those predominate, and both kappa free and kappa bound free are roughly proportional to rho over T to the 3.5 power, Cromera's opacity law. In other words, this is a log-log plot, and a power law plots as a straight line on a log-log plot. So each curve is a different rho. So for each curve, which has a fixed rho, the temperature is what's determining the plot. And these are all nearly straight lines in that region, where it's 1 over temperature to the 3.5 power, or in other words, T to the minus 3.5 power. So the slopes of these lines are minus 3.5 in these regions. That's the Cromera's opacity law. The other thing to say is, let's look carefully as we go from one curve to the next, okay? So let's go from the curve with, let's say, here 0 to the curve with 1. In other words, log density of 0, so rho is 1 kilogram per liter, to 10 kilograms per cubic meter, because here's the law of density is 1. Is that making sense what I'm saying here? This curve is rho equals 1 kilogram per cubic meter. This curve is rho equals 10 kilograms per cubic meter, because 10 to the first power is that one. How many kilograms per cubic meter for this curve? 100, 1,000, 10,000. Is the opacity proportional to rho? Well, let's look at a given temperature. Let's say right here, this temperature. Here I am on the 0 curve, and at the same temperature, here I am on the 1 curve. Right, about like that. What is delta y? How much did the logarithm change? Well, it went from about -1 to 0, from a little less than -1 to a little less than 0. So in other words, the opacity changed by a factor of about what? If I went, suppose I go from where the opacity is 10 to the -1 meters squared per kilogram. So right here, okay, I go up to the next curve at that same temperature, and it's right about 10 to the 0 meters squared per kilogram. So if I increase the density by a factor of 10, because every time I go from one curve to the next, I'm going a factor of 10 in density, I increase the density by a factor of 10, by what factor did the opacity increase? In this particular example, I went from an opacity of 10 to the -1 to an opacity of 10 to the 0. I went from 1/10 of a square meter per kilogram to 1 square meter per kilogram. By what factor did the opacity change when I multiplied the density by 10? The opacity changed by a factor of 10 also. 10 also. In other words, the opacity is proportional to the density. The fact that these curves are essentially all shifted by one dex, by one step in the logarithm. When I go one step in the density, the logarithm of the density, I also go one step in the logarithm of the opacity. That's showing the rho dependence, that these curves are all displaced by, these curves are factors of 10 in density apart, and they're also, for a given temperature, factors of 10 in opacity apart. That's exhibiting that the opacity is proportional to rho, and the slopes of the curves being -3.5 on this log law plot is showing the t to the -3.5 dependence. So if you didn't catch all that, look at it carefully later and sort that out in your head. And then 4, right here, there's a jump in the opacity at 40,000 Kelvin. Why? Because kappa free increases when helium-2 becomes helium-3, because now there's an extra population of free electrons around, and so there will be more free scattering as a result of that. And then, as you get to very high temperatures, everybody's ionized, and we, at very high temperatures, approach where the only significant source of opacity is electron scattering. So all the curves approach the electron scattering limit at very high temperatures, very deep inside a star, for example, because a stellar surface is never going to have a temperature of 100 million Kelvin. The hottest stars are maybe like 50,000 Kelvin. So when we go over here, we're talking about, now we're treating the opacity below the surface, deeper inside the star. Okay? So again, this won't be on the test on Thursday, but I want you to be able to explain this, why these plots look like this, in terms of what we've discussed today for the final. Okay? What questions do you have? Oh, glorious. I hope this wasn't too opaque to you. I'm totally transparent. It's a lot to take in. Maybe it will be that you need to look at this for a while to get it all to sink in.